Okay, so I kind of realized that I haven't actually been making any videos for you guys for a little while and looked back, and particle motion is just a topic that I haven't made one. So thought it might be worthwhile to take a look at that. So if you missed something, this will be highlighted on quite a few tests and quizzes over the next little bit because it's just an easy, quick application kind of problem. So anyway, let's just take a look at a couple of quick questions. And so here we go. See, hopefully this is going to work. I actually made this video already and it just didn't quite happen. So we've got kind of an interesting roller coaster here. It's like a vertical maybe roller coaster where you go in a straight line up and down maybe or side to side. It doesn't really matter, but it's governed by this particular velocity equation for 12 seconds. That's just kind of the ride, how long it will last for. So we're going to find the velocity and the acceleration of this roller coaster after t seconds. So of course, we should know that the derivative of your position function is your velocity function, which is, of course, not very difficult to do with the power rule. So we're going to go ahead and multiply the exponent by the coefficient and drop the exponent by 1. Similarly, on the second piece, and this particular one, it started right there at the origin. And that actually isn't really a bad thing to note, is that S of t right here, if you factored out a t squared, would be negative 0.1 t plus 1.2. So that gives you a little bit of an idea that if you were to find out where the thing is back, like what happened at 0 seconds and what happened at 12 seconds, I believe both of those positions come out to be 0. So when is the roller coaster stopped? I guess I haven't finished this next portion, but the acceleration is the derivative of the velocity, which of course is the second derivative of the position function, or negative 0.6 t plus 2.4. Okay. So the first question that we have is, when did this particular roller coaster stop? And of course, when a roller coaster has stopped, that's going to be the time when the velocity, which is negative 0.3 t squared plus 2.4 t, is equal to 0. And of course, factoring is definitely our friend in many, many places of mathematics. So it turns out if you kind of do a quick factor and notice that they both have a t in common, and if I pulled out that leading coefficient, you can very quickly find out that v of t equals 0 at both 0 seconds and at 8 seconds. And that actually makes sense on a roller coaster, that at time 0, you weren't moving yet. Otherwise, people would get a little bit hurt. So v of t equals 0 at t equals 0 and t equals 8. Now, we have a second little piece of this that asks about critical times. And the critical time is actually when the derivative is equal to 0 or undefined. So in this particular case, we actually already took the derivative and we found out where it was 0. This particular derivative is always defined, and therefore there is no other critical value other than the places where that happens. So it'd be t equals 0 and t equals 8. So I'm just going to write that down, that t equals 0 and t equals 8 are our critical values. Now, we have a little bit of a statement down here about speeding up and slowing down. And I'm leaving a gap right here for a reason that I wanted to look at. So one of the things that we like to do in calc is we like to make kind of a sign chart. And we know that our velocity was 0 at 0 and 8. I also know that this is a downsloping parabola, so it should be negative to the sides and positive in the middle. I also could look at my acceleration equation, which is right here. And if I were to factor the negative 0.6 out, I'd be left with t minus 4, making the acceleration 0 at t equals 4 seconds. And this is also a down-sloping line. So it would be down on the right and up in the middle. So when we're asking the question about speeding up and slowing down, I'm going to kind of use some color here. So speeding up happens when the signs of both the acceleration and the velocity match. In other words, I'm moving to the right and I'm accelerating to the right, or I am moving to the left and I am accelerating to the left. Whereas slowing down is the place where the values of those two things differ. Now, you notice that they would differ out here, but the roller coaster hasn't begun, so that would not be a relevant value. So the speeding up region is from 0 to 4 and from 8 to 12, because those are the regions where this particular roller coaster actually has been defined. The slowing down region, of course, is that little place in the middle there where the signs do not match, and that actually happens from 4 to 8, okay? So hopefully that's pretty easy. Now, one thing that I did want to find out is what is the total distance traveled by that roller coaster? So you'll notice that the roller coaster went forward from 0 to 8 and then backwards from 8 to 12. So if I wanted to find the total distance traveled, which is not a question that was actually originally phrased in this thing, I'd want to actually do that. So let's just see what we could do. I'm going to find the displacement from 8 back to 0. In other words, how far forward did it go? Notice that I put an absolute value on it because displacement can be positive or it could be negative. But when we would talk about total distance traveled, we just want the absolute value of that. And then I'm going to find out what happened from 12 to 8. And again, throw absolute value on that. So notice that I put my equation in there. And so let's just find out vars, y vars, y1 of 8 minus y1 of 0. And because it's going forward, this should be a positive value. So we went forward 25.6 units in this particular problem. I don't think it actually says what the units are, so we'll just say units, which is fine. But then when we do the other side, you're going to keep in mind that it should be an absolute value because it's going backwards. So I'm going to take the absolute value of y1 of 12 minus y1 of 8 to find out how far backwards we went, which, what do you know, happens to be 25.6. Of course, the roller coaster should start and end at the same place. That's how roller coasters always work. So we've got 51.2 total units of distance traveled. Okay, moving on to the second question. We've got a projectile that's been fired upwards with initial velocity of 96 feet from the tower that's 256 feet high. So we have a situation where something is right up here. It's going to be fired upwards and kind of come down and hit the dirt down here, something like that. So the magic equation that I went over in class is that your position function literally anywhere in the universe, which we found out, and this comes straight out of calculus and how it kind of just has to be, is we start off with 1/2 gravity times time squared. This is what happens in free fall. Now, if you put like a jet engine or something that actually modifies that value, we've got other fish to fry. But as long as it's free fall, in other words, some initial velocity was given, and then no other interactions are happening, we're actually ignoring wind resistance and things like that, but it's not too far off. So what we have is, since this is in 96 feet per second, and it doesn't say anything different, so we're going to assume this is on Earth. Gravity on Earth is 32 feet per second. So this is going to be negative 16t squared. My initial velocity right here was given to be 96 feet per second, and my initial height was 256 feet. So that's x of t. Now it says, how long will it take for that projectile to reach its maximum height? And the first critical thing there is to say, well, then the velocity would actually reach 0 at the place where that height is, because it's going to go up, it's going to stop just instantaneously and come back down. So we're going to take a look at v of t. And v of t would be, of course, the derivative of my position, which is negative 32t plus 96. You can see that this problem was obviously designed to be very, very gentle. If we factored out a negative 32 out of that thing, we would be left with negative 32 times t minus 3. And so we can see very quickly that the velocity was 0 at t equals 3, So t equals 3, v of t equals 0. So that's going to be the time at which that happens. That's going to take 3 seconds to reach that top value. And then what is that height? Now, keep in mind, when you ask for what that height is, that's actually not referring to velocity, but the actual distance off the ground. So we're going to be actually finding out what is x of, or your position function at 3. So if we were to plug in 3, negative 16 times 3 squared, plus 96 times 3, plus 256, turns out you can do the calculator work on that. That is 400 feet up in the air. So was it 256 feet up in the air, and it went up an additional, I believe it's 144 feet. So how long will it take the projectile to reach a starting point on the way back down? So keep in mind that if that's the case, we should know that if it took 3 seconds to get from here to here, it should be an additional 3 seconds to get from here to here. So we should know automatically that that answer is t equals 6 seconds. And it's just based on the symmetry of the curve. But what we could do is we could take our position function and we could say, well, x of t, let's see, which is this function right here. And we want to know when is it equal to the original height that it started off with, which was 256. We could clearly cancel those two things out. And we're asking then, when is negative 16t squared plus 96t 0? And we could do a little teeny bit of factoring, like pull out a negative 16 and a t. What would be left is t minus 6. And that leaves me with 2 times when this height is exactly 256 feet off the ground. And that happened at t equals 0 and at t equals 6. So you can see the validation of what our logic tells us it should be. So then what is the velocity when it passes the starting point on the way back down? Now, again, logic tells me that if it was going up at 256, it has to come right back through that same value on the way down. So I should know that v of 6 should be negative 256 feet per second. But again, we could just do v of 6 and literally take our velocity equation, which we have written right up here, which was negative 32t plus 96. And that does, in fact, give me negative 256. So you don't have to just trust your logic. You can actually go ahead and trust the equations that we've derived. So now the next question is, how long does it take this darn thing to hit the ground? Well, keep in mind, the ground has nothing to do with the building right here. It has to do with like what's going to happen right down here. So we're going to be finding out when is negative 16t squared, 96t plus 256 equals 0. Now, sometimes we get lucky, and in this problem we did. So we might just go ahead and try to do this right here. And again, I've made reference to this idea with you guys. Actually, never mind. I'm going to go this way. I'm going to go program quad. Now, my program just is designed to say, let's solve the quadratic equation where A is negative 16 right here, B is 96 right here, and 256 is, of course, C. And it says, hey, you're going to have roots at t equals 0, t equals negative 2, and t equals 8. And so that tells me, obviously, that it wouldn't have hit the ground 2 seconds before it was launched. It would definitely be 8 seconds after, and that's from the quadratic formula. But of course, we could have factored the negative 16 out, and if we did, we got negative 16 times parentheses t squared minus 6t minus 16. And this is going to validate our response that we had right there very easily. And you're going to notice that we're going to get those same two values. And so on all of these are word problems, so we should write a little sentence, but I'm just communicating that orally, that it would take exactly 8 seconds for this thing to hit the ground. And then, of course, the speed at which it hits the ground would be the absolute value of that velocity function evaluated at 8 seconds. Because remember, velocity is a vector. It can be positive, it can be negative, but speed is an absolute value. It's just a magnitude. So let's see what happens if we took negative 32 times 8 plus 96. So don't forget the fact that order of operations says we're going to put these two guys together first, and then we're going to add the 96 and then take that absolute value. So we end up with negative 160 or positive 160 feet per second as the particle hits the ground or the rocket or whatever it is. Hopefully that was helpful, and I will see you guys back in class. Bye-bye.